So the other thing that we did was we replaced silver with copper. We looked at the response to a sinusoid, pulsing, how does it look? And then we measured quasi-static DCID curves as a function of temperature from 5 Kelvin up to 350. And our hopes are to use this data to learn everything we can from that data about conduction, whether it's ionic conduction or electron conduction in that system. And the first test that we did this on is for the basic device, not the tungsten doped, but the basic structure. And I ended up taking out a lot of this data, but if there's popular demand, I can show it because it's at the very end of this slide. And the reason I took it out is it's still being analyzed, and those of you that are in this particular materials type area and looking at this, you'll understand how complicated it is, especially when you see things you don't expect. Like, for instance, the transfer coefficient is very temperature dependent. Is that an artifact? Is there something else I need to consider? Things like that. That's in there, but I can show you where we're at if you're interested. Otherwise, I'm going to leave it out until we know what we're talking about. The copper versus silver. In the copper case, what you can see is that after you raise the frequency up to 100 hertz, you get the flat line. The lobes collapse at a really low frequency. In the silver case, that's not true. You can see some lobing even at 10,000 hertz, really. And it's not until you get to 100 kilohertz that it starts to flatten out. Or maybe you see it is flattening a little bit more at 10 kilohertz, but definitely not 100 hertz. That's one huge difference. The second one is the copper devices in this structure, just replacing silver with copper, they're really slow. So you look at this, what does that remind you of? It's like, you know, what's happening here, what's charging here? But it's a slow response, and the silver doesn't have that behavior whatsoever. They're very fast. You can't see any delay in our measurement system. The copper, on the other hand, had a lot more control in terms of consecutive pulsing, a lot more. One of the things I will say about the copper system is it may be slow, but it's really reliable in terms of pulsing. So if I go and I show you this copper repeatability test, this is a 1 microsecond pulse applied to one device. This is only one device. But it was applied to the same device at random times. So I may take that device out, erase it, do things with it, come back and apply the same pulse sequence, and I get the same thing. It's beautiful. And I tried this random test for different pulse widths, and I always saw the same thing with the copper system. It was just fantastic, but slow. So the temperature dependence measurements that we have done that I will talk about, we did 10 devices at each temperature as we tested. So lots of devices were measured. My poor student was in that room for a long time. And there were DC quasi-static sweeps. And the test sequence was a DC sweep right, a DC sweep erase, and a DC sweep right again. So each one was set, I forget what the compliance current is, but we'll see it, probably 100 microamps or something like that. Set with the same compliance current, swept out to a high potential in order to capture all the switching. And just to look at the curves, just stepping back, looking at what was collected, I will say this is the general shape. So this is silver. The first right, the forming right, from room temperature, actually 350 K here in the dark trace, down to 5 Kelvin, this is what you see in your first right sweep. This is compliance current of 100 microamps. The second right looks a little bit different. Notice how things are a little bit clumped. We don't have a lot of the low temperature data. The reason is the second right wasn't available to many devices because they were damaged below 125K when they were operated. Just completely broke them. The copper, on the other hand, you can see you've got a lot more of this type of curve than you do in the silver. And you didn't damage any devices when they were operated at low temperature. It worked. So that was one positive thing about that. So the electron and ion conduction mechanisms are, understanding that data, it's underway. Let me see if I show anything at all. No, I don't. I almost feel like I'm robbing you of that, so I might go and just jump ahead and show you something that I want to show you. This is the resistance after the first write for the silver case. And in this case, you can see, notice your resistance is actually going down as you increase your temperature. Anybody know what that looks like? Semiconductor or metal, it's basically semiconducting behavior. And as you do this, you reach a point around 200 Kelvin where you're writing the device, it looks like you are because you're switching, but your resistance doesn't hold. So when you read it, you get something that's high resistance again. And then you reach a temperature around 125 or so, where it starts to write again, apparently. But what it's doing is breaking, it's being ruined. And the reason I want to point this out is these temperatures were predicted by the theoretical calculations that we're using for our device model. And they are temperatures corresponding to what's happening with the trapped electrons, the pair and the single trapped electron.